Hi, welcome to Sisyphus Crane and Rigging. It's part 2 of the Eponymous. This is Mr. Bix. Welcome to my channel. We pick up where the Eponymous 1 of 3 left off. We had just constructed the gripper. This video is the rest of the gripper mechanism. Then we start with the Z-axis. The arms were attached to a backing plate, and here it is. It needs to hold the pivot for the arms, the slot for the drive pin, then the motor bracket which holds the motor. I'll get to more about the motors in a moment. Also, it has places for the up and down limit switches, the belt cinch mount, and then the flag for, I call it a flag, for the limit switches that will be mounted on the Z-axis part. That flag will also hold the contacts for the moving connection, which is an assembly unto itself, a little tiny thing. And the countersunk holes attach the plate to the carriage. The pockets allow room for the motor and the bracket. So here I'm milling the vertical backing plate, basically a little block of aluminum with holes and pockets and threaded holes and stuff. With the block done, I still need a tiny little motor bracket. It's just a little piece of bent metal with holes and slots. I start by milling a strip to the width of the bracket, then bend it over 90 degrees, and then at some point along the way I cut it to length. I like to get a nice square bend and then come in, take a zero off the edges, and then you get accurate slots and holes, and you can cut it down at any point in the process. Alright, so I need a spacer of about 500.568, so I grab a, what's going to work, a 450 and a 118. Alright, and that's going to add up to 568. Come back over to the mill. And this is gauge block abuse, but they're already abused and they're no longer ever going to be gauge blocks, and now they're spacers. And boom, the vise is even and this thing is parallel. Good. Now we'll do those holes and actually poke them. But the first thing you got to do is move those parallels out of the way because they'll get drilled. And I'm going to use this little end mill as a drill bit. This material is 5052 aluminum sheet, 40 thousandths thick, about 1 millimeter. I use that because it's bendable. It's also highly corrosion resistant, although I don't really need that for this application. If you use 6061, which is kind of a go-to material in aluminum, it tends to crack when you bend it. So I'm milling out the circular hole for the motor clearance. And there she is. I'll trim the back and front edges to the right size and we're done. Alright, so with the parts made I can check the fit. That's going to go in there, and I've got screws to attach it. These are 172s. In general practice I'm going to try to use SAE hardware, except where I use a part that's got a metric threaded hole. In the case of this motor, it's got M1.6s. Alright, so that bracket fits in there nicely. Well, it gives me a little bit of adjustability. And of course that's going to go through there, but I can't put it on until I cut the lead screw to the correct length. I guess that's next. If you do a search online for N20 motor, you'll get a lot of these things showing up. I got mine on eBay. They come in all configurations and a range of speeds, as you can see. The one I'm using is a lead screw motor, and it just has a M3 metric lead screw, and I put a nut on it, drives it back and forth. So I put a baggie over it, and I'm cutting it with the Dremel tool. The baggie obviously keeps the shards out of the gears, you know, little chips and so on. I'm just using a Dremel with a heavy-duty cutoff wheel. And you got to be careful about side loading those things, of course. They tend to be very fragile and they're spinning, so they'll fly right into your face if you break them. Clean up the end of the shaft with first just a little bit of grinding on the Dremel, or you can go to a grinder. And then I like to go to the Scotch-Brite wheel and kind of go around. kind of rotate the face of the edge of the lead screw or whatever I cut off, shaft or whatever, around the edge of there so that it cleans it up. And I put the nut on beforehand so that when I take it off, it'll hopefully carry any little burrs away with it as well, making sure that I can get it on and off. And it's important to get them square. You saw me cutting it square at the end there. And pull the nut off. I'm ready to install this thing. So I'm milling out a block here on a part I call the nut link. It captures the lead screw nut that goes on that lead screw, that M3 nut. And as well as holding the nut, it provides for a way to hook up to the drive pin of the gripper, and has an arm sticking out that presses the limit switches for the up and the down positions. So I just lower the Z-axis and jog back and forth with the X or the Y jog wheel until I get it to the thickness that I'm looking for. I probably went to points that I'd already determined by math on what size to make it. So here in the Bridgeport pendant, I've got the layout and I've plotted the points for the endpoints of the mill line sequences that I do to make that pocket. And I program that into the mill, one mill line step after another, using the endpoints that I plotted, X and Y endpoints. And if you thought I was driving that a little too fast, you were right. It's a 1/16 end mill and broke that one right off, so I got to go a little slower and not plunge as deep. Anyway, with those points plotted, I just keep going around until that nut fits in there really snugly. Now there's a view of it in SolidWorks. You can see how it captures the nut. It has round pockets at the corners, but I didn't end up using those because I figured the nut corners themselves aren't that square. And besides, I was sneaking up on it, making a new program each time. And when it pressed in snugly, I left it. I've got a provision to put a set screw on the side if need be, but I haven't put that in yet. So there it is with its limit switches. That pin will be cut down later. And I think you've seen it work in other videos. So that gripper piece and the moving part of the Z-axis is done, except for rewiring it, which I'll do. It's going to need a backbone and a way to connect to its carriage and a way to connect the rail to the system. Here I've shown how they go together. There's the carriage, then the rail, the backbone. That's the gripper that grips the belt, which rides on the pulleys. Here the pulleys come 1, 2, 3, 4. And then we'll put in the belt. And I've devised a way to snug that in place. The motor on the other side. And also the up and down limit switches for the Z-axis and the sliding contacts. That long piece is the circuit board for the sliding contacts. And that's the flag, that last one that went in. And it's actually holding the contacts that move, as well as a way to press the switches up and down. And in that case, I have a screw on the up limit switch. So the screw reaches up and hits the arm of the limit switch first. So then I go back to that backbone part, and I'm just showing some milling. I drilled these out. They're actually blind holes. And then I'll tap them for attaching things on the side. I've got some places to put wire maintenance hardware and a way to connect the cover and so on. So I just drill and tap these out. And I also show a little bit later how I've got to drill and tap the ends. The pulleys go on the side of that to hold the belt. And of course they need shafts and bearings. I tried bronze bushings, but they were a little too sticky, so I put in little tiny ball bearings with the 3mm shaft size. I was able to fit 2 of those in each hole for the shafts. And this is how I made the shafts. took a little washer, a stainless steel washer, and milled out an interpolated circle just slightly smaller than the end of the shaft. And then I pressed it onto the end of the shaft, took that thing over to the lathe, and squared it up with a piece of plastic so it was nice and square. Then I applied a little bit of flux and silver soldered it. The flux was very crusty and I just went with it anyway, but I've since got a mortar and pestle and ground it much finer because it tends to dry out. You can see I'm applying it with a screwdriver, and it's about the worst method I can think of. It tends to melt into a glass-like substance on the surface of the parts that you want to solder. But once you get enough on there, it works really well. But that's the only video I have of it, so I'm just kind of showing how I got that flux on there. And then you heat it up glowing red hot, really. Don't let the solder touch the flame, and it'll flow right around there once it's hot enough. Here she goes. And some of these came out a little better than the others, but this was the first time I've ever tried to solder like that with a camera over my shoulder. Then I turn off the backside face of it, make sure it's clean on the underside shoulder, and they're ready to go. I wanted a very thin washer on the end so that they would fit under the switches and whatnot that's attached on the other side of this block. And then a little bit on how I milled the end pieces, because it's got to be held to the base block, and as well as it's got to hold the rail on the face of it. I used some stand-up 1, 2, 3 blocks and double clamped them with that extra clamp there. Power tapped them, blind holes. In many cases, they broke through other holes that I had already drilled. These holes are for the rail attachment on the face of it. Then I like to finish them out. I was hand turning them in the mill there. You put it in neutral and hand turn them, and then finish them out on the bench. Plus I used the little wires to dig out the chips. And I'll have to admit that sometimes chips are left in under the screws. So if you take apart any of my stuff, you might find little chips in there. But mostly I get them out. These are really tiny. I think those are 172s. And now I'm doing the other side. I have to be very careful that they don't crash into shafts. These weren't so bad on the bottom, they're 440s. Trying to be efficient and use the tap magic that's kind of bleeding out around the top of on the lid of the can. And again, just turning by hand well before they hit bottom. I take it back over to the bench, finish them out by hand again. But now that they were done in the mill, they were started in the mill, they're very straight. So there I put it together and ran it. There are slots where the motor mounts so that it can be tightened against the belt to keep the belt to the right tension. Then I installed the capture block. This little thing that grips the belt, and it's got slots so it's adjustable so that I can fine-tune the position. It's made in 2 parts, one that attaches to the moving block and another one that actually tightens against the belt. Fussy little parts to make, but it grips the belt rather nicely. I put teeth into the face of the one side so that they mesh with the teeth of the belt. And that's what drives this whole thing up and down. That's the capture block there. Two more little odd 80 screws, and you can see it's captured and adjustable. So now I get to run it. I haven't wired it finally yet, but it drives up and down and it's hitting the stops, the switches, so it knows when to stop and be reversed. This is the belt side. And all those wires are going to have to run over to the little sliding contact system. They won't be that big. A bit of belt lag right there that I got to fix. And that's coming up, how we build that little thing. the sliding contacts. That wraps it up for this video. I hope you enjoyed it. Keep an eye out for the next ones. And as usual, I like to pose the question, is it not absolutely original? And I've got an absolutely original link for you. It's J.F. Scalbert, or Scalbert. He's in France, he's a kinetic artist, and definitely an original. Check him out, the link is below. Thanks for watching.